Okay, welcome to the next class on multiple view reconstruction, the next lecture. We're finishing off where we left off yesterday. What we talked about yesterday is reconstruction from two views. We talked about the 8-point algorithm. We talked about structure reconstruction, so not only recovering the camera motion, but also recovering the 3D geometry of things. We talked about the 4-point algorithm that uses homographies and that works with the assumption that the world is planar, or that the points that where we have correspondence all belong to points that live on a plane in 3D. And we saw that this is a very strong assumption that leads to the 4-point algorithm. The last part on the two-view scenario that I wanted to mention is the case of uncalibrated cameras. What I mean by uncalibrated cameras here is that we have a camera that takes images. We have the images, but we don't have the intrinsic parameters of the camera. In particular, as you may recall, there is the calibration matrix K. It has the focal length F in it, and it has these parameters, the scale parameters, these pixel sizes SX, SY, the offset of the origin OX, OY, and possibly some skew factor there. So there is a 3x3 matrix that models these intrinsic transformations that the camera does. And the question is, can we do uncalibrated reconstruction? Can we recover the motion of the camera and the 3D structure even if these parameters are not known? The question is, when does this scenario arise? It typically doesn't arise if you have your own camera. Because if you have your own camera and you want to do image-based reconstructions with your own camera, then you would typically calibrate it first. The way this works is, we didn't talk about it extensively in class, but there are standard algorithms even on the web that you can download to calibrate the camera. And what you do is you have a checkerboard pattern, and typically even that is online. You can download it, print it out. Then you have a checkerboard. You take images of that checkerboard, and then using these images you can estimate the camera parameters. And so basically you calibrate it by taking pictures of a known structure. And since you know what the structure looks like, you can estimate these parameters. The scenario we're looking at now, the uncalibrated reconstruction, is a scenario that is useful if someone gives you the images, but that person does not give you the camera parameters. Usually because they don't have them. For example, if you go on the internet and you download images, chances are you just get the image and not the camera parameters. And then you have a setting of uncalibrated reconstruction. Just a second. Sorry, I hate this. Yes, that's the uncalibrated reconstruction case, and the issue there is that we don't have the camera parameters. On the internet, actually, interestingly, if for certain data sets on the internet or images you download, often these camera parameters, or at least some of them, are captured in the image and they're stored with the image. So good cameras often store these camera values. Once they store the digital image somewhere in the image format, they also store things like the focal settings. Not always, but sometimes. Another scenario is, let's say you have old movies and you want to recover, say, the house where Vivian Leigh walked down the stairs in Gone with the Wind, for example. Then you have these images, but no one tells you what the camera was. No one tells you the parameters of the camera. And in that sense, you have then the uncalibrated camera. You still want to recover geometry and camera motion, but the question is how to do it. And I'm not going to spend that much time on it in this class, but I did want to point out how this works on just 2 or 3 slides. So the idea is that we have this intrinsic matrix that we typically ignored in the past, K. In the last couple of lectures, we ignored that matrix K that we have in here, and the fact that we have coordinates which we call x prime. These are the image or pixel coordinates. So that is really the 2D coordinates in pixel coordinates. And what we've done in the past slides, we called it x, and x were the normalized coordinates. That were the coordinates obtained once I removed these calibration aspects. Just by multiplying k to the minus 1 to the observed to the pixel coordinates, I get these normalized coordinates. And then I have this epipolar constraint that is defined on these normalized coordinates. If you don't have k to the minus 1 and k, the question is what you can do, and here's how you can tackle the problem. Here's the epipolar constraint. So we now assume we don't have the camera parameters k, so we have a reconstruction from uncalibrated views. We have the image coordinates. These are pixel coordinates, but we don't know what normalized 2D coordinates they correspond to. But what we can do is we can rewrite the epipolar constraint. Here it is. These are the 2D coordinates, x1 and x2, the normalized ones. And here's the essential matrix T hat R. And there's the epipolar constraint that we saw over the last couple of lectures. And now we can replace x1 and x2 by, as you can see here, we replace x1 by k to the minus 1 x1 prime. So the assumption, mind you, is that it's the same calibration matrix for both images. I mean, in a nasty case, you could have a scenario where from one image to the next, the focal settings change. That's very nasty in some sense. Then you would have 2 separate calibration matrices for the 2 images. Here, we assume it's the same intrinsic calibration for both images, but we assume it's not known. And then you see we get a very similar constraint for these image coordinates or pixel coordinates. So it's essentially another bilinear constraint here. But in addition to T hat R, we have k to the minus t, that is k to the minus 1 transpose, and here k to the minus 1. So we multiply from left and right with k to the minus 1 transpose and k to the minus 1, multiply this essential matrix E. And that constraint, that matrix that we obtain, so we can compactly write it in this way. So we have these image or pixel coordinates in the first and the second image, and we have in between a matrix F, a 3 by 3 matrix F, and this matrix is called the fundamental matrix. Why it's called the fundamental matrix, don't ask me. My suspicion is whoever invented it had a sense for marketing. That's usually the reason why things have bombastic names. But it's, of course, of central importance for the reconstruction in the uncalibrated setting. So maybe it's acceptable to call it fundamental matrix. So the matrix F is this matrix, and now you see it's a matrix that contains not just the camera parameters, rotation and translation, the so-called extrinsic camera parameters, but it also contains the intrinsic camera parameters in this matrix K, or its inverse. We already talked about the structure of essential matrices, and we saw that essential matrices are matrices which have 2 equal singular values, and the third one being 0. So matrices in particular that have rank 2. We also talked about the fact that if you multiply a matrix with invertible matrices from both sides, that does not affect the rank, because this matrix is invertible, so the number of linearly independent columns or rows is not affected. Meaning, if E is of rank 2, F is also of rank 2. So we know whatever that fundamental matrix is, it is a rank 2 matrix. So it has two non-zero singular values. Unfortunately, though, these in the general fundamental matrix will not be the same. So we know we have a singular value decomposition with the diagonal matrix sigma 1, sigma 2, and 0, but we cannot say that the larger two are equal. They can be different. In fact, you can even show that any matrix, 3 by 3 matrix of rank 2 is a fundamental matrix. So for any matrix of this structure with two non-zero singular values, so any rank 2 matrix, there exists a rotation translation of the camera and intrinsic parameters such that this is equal to F. So the space of fundamental matrices, in other words, is a space that is substantially larger than the space of essential matrices. And in fact, you can imagine what we did in the 8-point algorithm is we used a number of such constraints more specifically, and then we estimated this matrix E in between, and then we determined from E translation and rotation. And we already saw that that was quite challenging, that for even once we have the essential matrix, there were multiple solutions for translation and rotation. Overall, there was a total of 4 possible solutions for rotation translation. 4 is okay because you can still then typically determine which of these 4 solutions is the right one. Here you can imagine once I mix the intrinsic parameters into the game, all of a sudden from the estimated 3 by 3 matrix F that I can estimate in quite the same way, just by using multiple corresponding point pairs in the images, I can estimate F with an 8-point type algorithm, but then to extract these parameters is more difficult. And there's going to be more ambiguities, there's going to be multiple solutions. And so this is what I marked here. These are in some sense the limitations of how far you can get in the uncalibrated setting. It is straightforward to estimate the fundamental matrix. You apply the 8-point algorithm to the image coordinates. That gives you in the same way the matrix F. But then once you proceed from there, how to get the camera motion out, how to get the intrinsic parameters out, this is more difficult. What I mentioned already is the fundamental matrix. The space of fundamental matrices is large, so even in the estimation, we cannot impose such strong constraints. So the whole estimation is less constrained. In the essential matrix, we could fix the 2 largest singular values and set them to 1. The smaller one, we set it to 0. That really constrains the estimation process. Here, we can set the smaller singular value to 0, but the larger ones, they need not be the same. And then even further, for a single fundamental matrix, there is not typically a finite number of possible interpretations in terms of rotation, translation, and intrinsic parameters k. Even apart from that global scale factor that we always have as an unknown, and that will always remain unknown in image-based reconstruction, in addition we have other degrees of freedom which provide that you have an infinite family of possible reconstructions. And these are typically called projective reconstructions. These are reconstructions of the geometry and of the camera position, rotation and translation of the camera, which are defined only up to a so-called projective transformation. And among these, there is typically a way to choose what's called a canonical reconstruction. So from the whole family of possible reconstructions, you choose a canonical one. Much like with the essential matrix, once we have to fix the scale, we can arbitrarily set it. We can define we want the baseline to be 1 meter or 1 centimeter, whatever, or relative to the size of our screen. We can normalize things. Similarly here, you can normalize the reconstruction and then select one canonical one. Whether that actually is consistent with what you have in the world is not sure. Much like once I fix the baseline and say I set this to 1 meter, it doesn't mean the real world is of that size. It means I just don't know, so I have to fix something. And so in this way you can do uncalibrated reconstruction, but it's much more challenging. And the consequence is that nowadays when people do reconstruction, they typically put quite an effort into getting the camera parameters, the intrinsic parameters. Because then you can normalize things and then you can do calibrated reconstructions. Okay, that's the end of slides part 5, and now I'm coming to part 6. Part 5 was on the 2-view scenario, and part 6 of this class, chapter 6, is on the reconstruction from multiple views. This is a fascinating problem and an important problem. The reason why it is important is that once you have more than 2 views, you have more information on the scene. You see the same structure over and over from different views, and that the more views you get, the more you have constraints on what is the possible reconstruction. And this is something that we all know from our own lives, that if we see something and we're not sure what the geometry is, we walk around it. We look at it from different viewpoints, and as you know from experience, the longer you look, the more sure you are what the geometry looks like, because you get novel views, novel information that constrains the possible solutions to the problem. And so here are the different parts. First, I want to say a little bit about why going from 2 views to multiple views is useful, and then there are additional parts on how we can generalize the 2-view setting to multiple views. And we'll see actually that there are different ways to do that. So we now assume we have a static scene, so we're still working in a static world, and the only thing that moves is the camera. But now we assume we not take just 2 images from the scene, but 3, 4, 5 images. And these can be taken, there are many scenarios for multiple view reconstruction. One scenario, and depending on what scenario you work in, typically you nowadays choose different algorithms. One is the so-called online scenario, where I have a running video camera and I move it around and it captures different images from different viewpoints. And the other one is that I take, if I want, for example, high resolution images, megapixel images, typically video cameras have a bandwidth limitation. If they take 60 frames a second, there's only so many pixels that you can transmit there. But if you go to higher resolution images, megapixel images, typically you will have a camera, you will walk and take pictures, individual pictures from different vantage points. These scenarios are different in that in the first scenario of the running video camera, I get tons of images, meaning the number of images is not an issue. I get 60 images a second if I like. And so I get more images than I can typically handle in a real-time scenario. And so speed is an issue, processing time is an issue. On the other hand, these images typically are the small baseline setting, because I move the camera only so fast, and when I take 60 images a second, it means that from one image to the next, the viewpoint hardly changes. So I have a small baseline, which is good and bad. It's good because I can track points more easily, I can associate and find correspondence more easily, but it's bad because if the baseline is small, the accuracy of the reconstruction is also limited, the precision. And in the other scenario, I typically have fewer images. and then it's typically involved, and so I typically only have 20 or 30 images, and then I have wider baseline, but then I have higher resolution in space typically, but lower resolution in terms of the number of images, so lower resolution in time, if you will. The idea of going to multiple views is that I have additional constraints, and it's actually quite easy to see that. You can actually write down what are the unknowns and what are the knowns, how much data do I have, how many measurements do I have, and how many unknowns. And the unknowns are typically large X, Xi, so these are the 3D points that are unknown on the structure I want to reconstruct, and then what I have are the 2D coordinates. The other unknown is the camera motion. So here is rotation, translation to the next camera. And then if I have a third camera, let's say I have again rotation and translation here. And these are 6 parameters. So every time I get a new image, it's another 6 parameters that enter the game, because it's another camera motion that is unknown. On the other hand, what do I gain? I gain a lot of 2D point coordinates, and so a lot of additional measurements for only 6 additional parameters. So the ratio of measurements compared to number of parameters to estimate gets better and better the more images I take. But of course there's a trade-off, because if you take tons of images, then there's a matter of having too much data, so it gets more involved to process all that data. And indeed, one of the challenges in 3D reconstruction nowadays, especially, I mean, one of the last classes, one of my students presented work on time reconstructions of actions over time. The major challenge is there is nowadays that you work with tons of data, lots of images and lots of reconstructions at every time. Let's say if you do 30 frames a second, 30 times a second you have to reconstruct an entire geometry, and so it's a lot of measurements and a lot of data to estimate. But typically, considering more images stabilizes the whole process. So the estimation of motion and structure will generally be more constrained. Interestingly, when going from 2 views to multiple views, people go gradually, and that's typically a good idea in science, that you go step by step, that you don't treat the full-blown general problem in the first day, but you go little by little. This is something I always recommend in research, to go step by step. I mean, you go upstairs by going step by step. You don't try to jump to the top in one go. It's typically not doable. And in the same way, people have started with the 2-view case. We saw a lot of work on that. And then they generalized to the 3-view case. So, but then typically, once you get the picture, you go from 3 to M views. And this is what we're going to do as well. The 3-view case has been addressed by the so-called trifocal tensor. So this is a term that I thought should be mentioned here. It's the trifocal tensor that was propagated by Hartley and Vieilleville and others. It generalizes, it's the direct generalization of the fundamental matrix. If you have 2 images, the fundamental matrix is involved in the constraint coupling the 2D points of the 2 images, and similarly you can generalize to 3 views, and then you have a so-called trifocal tensor. A tensor, for those who don't know, is the generalization of a matrix. So a matrix is a 2-dimensional structure, a tensor is 3 or more dimensional. And the trifocal tensor is a 3-dimensional structure that couples the 2D point correspondences in 3 views. And similarly, like with the fundamental matrix, that tensor does not depend on the 3D structure, but only on the motion of the cameras. So the motion from the first to the second, and from the second to the third image. And so, and these relationships among the 2D coordinates of points in the three views, this relationship is, there are so-called trilinear relationships, and these are captured in the trifocal tensor. And as you can see, these were studied in the 80s, in the late 80s, and then in the 90s as well. So there's been a lot of work in that domain over the years. There is actually two, I would say, competing approaches to how to model these relationships in three or more views. And one is this more traditional approach of looking at trilinear relations among triples of images, and the use of tensors, as you can see, was promoted by Villeville in 93, and there were a lot of people who contributed to work in that area. And then there is extensions to four views, so there's bilinear, trilinear, and quadrilinear constraints. These were developed by Bill Triggs in 95. And all of this work is actually summarized in textbooks nowadays. So this is typically, you can see how things go in science. People develop things in the 80s, in the early 90s, and then about 5 to 10 years later, people summarized all this kind of bulk of knowledge in textbooks, where they kind of review the state of the art and summarize it in a way that makes it a little bit more comprehensive and accessible to students. And these are two well-known books in the literature from 2001, Faugeras and Long, The Geometry of Multiple Views, and Hartley-Zisserman, Multiple View Geometry. There's by now 2 editions of that book out. And I should say the Hartley-Zisserman in particular has been used quite extensively by many people. And so that line of research that extends from the from the epipolar constraint, from the essential matrix and fundamental matrix to these trifocal tensors is summarized in these books. There is, however, a different approach to it that is to some extent equivalent, but is formalized differently, and that is an approach that doesn't need tensors, but it uses matrices. So we can actually stick with matrices, and instead what we will see, and this is the approach that we will pursue in this class, it is an approach that was proposed by a number of people, among others by Bill Triggs as well, by Hayden and Ostrom. And this line of work is summarized, is the basis of the Ma-Soato Koseka Sastry book. And so the difference is that we can stick with to a certain extent with matrices and with the formalism that we know. And then instead of having an epipolar constraint, we will have respective constraints on the rank of matrices. So let's go into it now. The pre-image of multiple images of a point or a line is the largest set of 3D points that give rise to the same set of multiple images of that point or line. So what we do now is we go back to the notion of pre-images a little bit in more detail. Maybe I'll show you the drawing first so that you get an idea of what we're trying to do here. What we do is we consider 2 scenarios. One, we consider the case of observing points. So here's a point P that is being observed in 2 images, and we'll see in a second we can generalize to M images. And we will also consider the case that we observe lines in 2 images. Why do we separate these 2 scenarios? Well, the aspect of lines is interesting because it shows you what information you gain from going to multiple images. Yes?
Should the lines be straight or?
Yes, straight lines. So it's not a curve but a straight line. That is a straight line in R3 that is then imaged from multiple views. And here's the thing. Assume you see a point in 2 images. And assume someone gives you the camera transformation, then it's not guaranteed that you actually have a consistent pre-image, because these lines, these extensions, these rays going through these points may not always intersect. Instead, if you look at lines in two views, then the pre-images always intersect. If I have two planes, they always intersect. Of course, in the worst case, they intersect somewhere at infinity, but there is always an intersection. So there is always a consistent pre-image once I observe two lines. For the observation of 2 points, that is not guaranteed. Meaning, if I say, oh, the reconstruction, in order to have a consistent reconstruction, I want that there is a pre-image, that is not a constraint once you look at two images of a line, because the pre-images always intersect. However, if you have 3 images of a line, you can imagine, let's say you have a third image of a line, then it's not sure that they all intersect in a line in 3D. And so when you look at lines and you say, I want a consistent pre-image, then having 3 views of a line actually is a non-trivial scenario where there's not always a pre-image. And this is why we study the aspect of lines in multiple images separately, because there it's more obvious that multiple images actually help, and that imposing the constraint that there should be a consistent pre-image is a non-trivial constraint for 3 or more images. So how do we tackle that? Some notation. We have a line here. There's a point P on the line. There's some base point P0. Here's the line. And then we have these observations of the line in 2 images. And the idea of tackling the pre-image, we talked about pre-images for 2 views, and said for 1 view actually, we said the pre-image of a point, for example, is the line of points that are possible reconstructions. These are the points which map to the same observation. And we can similarly define pre-images for multiple views. And it's very trivial actually. We say the pre-image of a point observed in m images, so x1, little x1 to little xm are the m observations of that point. The pre-image of all these observations is nothing but the intersection of these pre-images. So I have one pre-image for this point and one pre-image for that point, and the intersection is ideally then my reconstruction. Or it is if it's so that is the set of feasible reconstructions. And the idea is the more pre-images, the more images you have, and the more pre-images you can intersect them, and by intersecting all of them you can constrain the reconstruction more and more. And similarly, you can have lines. L1 to LM are if we go to the drawing, these are the lines observed in the 2 images. And then we can define the pre-image of these as the intersection of the individual pre-images. And so the extension of pre-image to multiple frames is simply done by intersecting all the pre-images. And of course you can imagine, once you have multiple images of a line, then the intersection of pre-images, there are many possibilities. One is that it's the empty set, that if I intersect all the pre-images, nothing remains. The second scenario is that the intersection is a single point. So if we go to this drawing, assume there is another view of a line. If I intersect that, possibly there is going to be one point where they all intersect. Possibly there is a line in 3D, and possibly the intersection is empty. So there are different scenarios for what can happen once I intersect the pre-images. And of course, these observations of the line are consistent if and only if there is a line in the intersection of pre-images. So if I observe a line in 3D from multiple images, these pre-images have to intersect in a line to get a consistent reconstruction. And so we will see later we have constraints, and we can formalize the constraints in such a way that we say we want the pre-image to be a line. Once we talk about lines, we will typically also talk about that this is the pre-image. So if we have this line in the image, then its pre-image is this plane P2, and the plane is defined by a normal vector L2 that is normal to the plane. So I hope you can see the visualization. L2 is the vector that defines the normal to that plane. And so now we consider a moving camera over time. At time t, x of t is the image coordinates of a 3D point x. So we observe a 3D point x in the world from multiple views, and we saw this projection equation already. The depth lambda of t for time with respect to the camera at time t times the 2D coordinate is nothing but the large point rotated, translated into the camera coordinates at time t. Pi 0 is the generic projection, and k of t are these intrinsic parameters of the camera at time t. Now consider a 3D line. A 3D line, if we write it in homogeneous coordinates. Why homogeneous coordinates? Because this projection equation is in homogeneous coordinates. So here, large x is a 3D point, but the fourth component is 1. So that is a 4D vector, where the 3 components are the 3D coordinates, and the fourth component is 1. And so we will represent the points of the line in homogeneous coordinates to work in this representation. And so these are points large x, which are simply obtained by having a base point x0 plus mu times an offset vector v. And since all of these points should be homogeneous coordinates, the offset vector, of course, has the fourth component being 0. So that if I add multiples of that vector to x0, the last component will always be 1. So we always have homogeneous coordinates. And so we have a base point, x0, y0, z0, 1. So that in the drawing would be this point here. And then we have a vector that models the displacement v1, v2, v3, and last component 0. And if I go through all possible scalars mu, then I get all points on that line, obviously. And this vector v is the direction of the line. So this is a representation of the line. So I parameterize the line with a base point and an offset vector. The base point is x0, the offset vector is v. And now I consider pre-images. We said the pre-image of the line is this plane P. It has a normal L of t, and since the camera moves over time, this normal vector changes over time, and P is spanned, as you remember, by L hat. L hat is this skew-symmetric matrix. It contains the vectors that span the plane. So the two vectors that are orthogonal to L. And the vector L is the normal vector on the plane. It means in particular that it is orthogonal to all points xt of the line. So if we go back to the drawing, here is the points xt on the line, and as you can see, that normal vector, no matter what xt I take, what point on the line I consider, the normal is always orthogonal. Meaning the scalar product of L with xt is 0, and that means L transpose times this here, k pi 0 gt, that is is 0. So what we've done is we've just taken this expression and basically this equation and projected it onto this L that defines that is the normal on the pre-image. And now to simplify notation a little bit, I will call lambda I, lambda at time ti, so that is the depth with respect to camera I. This is the coordinates in camera I, etc. And pi I is the projection onto the camera I. And so I have in shorthand the 2D coordinates times lambda I is the projection matrix times the 3D point, and what I get is, once I insert that up here, I get that Li transpose pi I x0 must be 0, and Li transpose pi I v must be 0. Why is that? Because for any point x on the image, on the line, this Li transpose times this is 0, and then I can select mu equals 0. Mu equals 0 gives me the base point on the line, x0. So if I insert x0 in this equation, then I get Li transpose pi I x0 must be 0. And then for any other mu I see, say if I said mu equals 1, then I get Li transpose pi I v equals 0. Which means I have actually two constraints, one constraint for the base point and one constraint for the offset vector. Yes, I think I'll stop here and we'll continue next week. Thank you.